Welcome to 58 Reflections. So remember last time we did 57, which was translations. That's when you're moving things up, down, left, right. Today is reflections. Both of these fall under the general category of transformations. So that's the general topic, transformations. And actually next time we'll have a third kind of transformation. But anyway, we're talking transformations, and today in particular we're talking reflections. And to be a little more specific, reflections over the coordinate axes. We are kind of limiting ourselves to reflections over the coordinate axes. In other words, you could have, like there's the x-axis, there's the y-axis. You could have a parabola like this, and if you reflected it down over the x-axis, it would end up looking like this, right? That's the kind of reflections I'm talking about. We're not talking about this kind of a reflection where you have the parabola like that and you kind of reflect it over its vertex or something. We're not talking about that. We're talking about the axes, reflecting over the axes. So anyway, get these scribbles out of the way. Now, in order to take a look at these things, we got to start with a basic function, and this one's not quite so basic. It's a straight line. This fits the pattern of mx plus b, you might remember. So this is a line with a slope of 1 and a y-intercept of 2. So let me just take that shortcut to draw it real quick. I said the y-intercept was 2 and the slope was 1. So from there you go up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, down 1 back, 1 down, 1 back, 1 down, 1 back, 1 down, 1 back, and so on. So there's our, I think I'll label it. That's our function f of x. So you don't have to start with such basic. You can, when you're doing these transformations, you can start with whatever function you feel like starting with. So I feel like starting with a line. So, okay, we'll start with that line. Okay, the real question is, what happens if I build a new function, g? I'm going to build it out of this f function. I'm going to take the f function, and in particular, I'm going to do this to it. What am I doing to it? I'm taking that f function, and it looks like I'm basically multiplying it by a -1, right? So this is kind of like, maybe I'll even say it that way, multiply g of x by a -1. And so what does g of x look like? Well, if you were to multiply this by -1, what would you get? Careful here. If I were to multiply that by -1, I would get this. Did you get that -2? You're multiplying the whole thing by negative, right? What's that look like? It's like when you do -1 times the whole function. So you're distributing, right? So you're getting a -x and a -2. So just be careful about this kind of stuff. So anyway, we don't have to make an xy table to graph this because this is in slope-intercept form too. This has a slope of -1 and a y-intercept of -2. Let's just see what that looks like. And actually, I'll graph it in a different color. So let's see, y-intercept -2. Slope of -1, down 1 over 1, down 1 over 1, down 1 over 1, up 1 back, up 1 back, up 1 back, and so on. So if you connect all of these points together, you're getting this new line over here. Now compare the blue line, this is my g of x, compare the blue line, f of x, and this orangish brownish line, g of x, and keep in mind I'm trying to show you a reflection here, and ask yourself, well, which way has this been reflected? And again, we're talking about reflecting over the axes. It looks like we're reflecting like this. Reflect sort of from up to down. Reflect over the x-axis. So this point up here at y equals 2 is coming down here to -2. And this point up here at +4, y equals +4, ends up down here at y equals -4. See what I mean? And it works the other way. This point is at -2, and it's reflecting up to +2, or at least it would if I drew it right, and so on. So this is a reflection over the x-axis. That's what this does. So let's just kind of remember that somehow. Huh? Let's say. I guess I'll say the effect of negative times the function is to reflect. And in fact, I got a shorthand way of saying that. I might as well start using it now. is to reflect over the x-axis, which, to emphasize that I mean up and down, you can put a little arrow like that, up and down. So the effect of this negative in front of the function like that. So again, this was the function. This was the function. I put the negative in front and multiplied the whole function by -1, distributing and everything, okay? That's the effect here. So if you put a negative on a function, it's going to reflect it up and down like that. Can you dig it? Can you dig it? Okay, now let's get this stuff out of the way. Move away, you bother me. Ooh, I was afraid of that. I was afraid of that. Okay, let's put our blue function back, lest we forget, lest we forget. So, this won't take too long. It was going through here, right? Yep. That was our original function. Ah, that looks terrible. Try to get it to line up with the grid a little better. There we go. So it has a slope of 1 and a y-intercept of +2, right? That's what this had. Slope of 1, y-intercept of 2. Well, now let's look at this over here. In fact, let's change colors and look at that over there. So what's going on here? Well, notice the negative's in a different spot. Over here, the negative was out in front, and that meant multiply the whole function by -1, which is not what's going on here. What's going on here is go inside the function and make x negative. Make all x's, really. Take every x inside your function's equation there and make it into a negative. Okay, what does that mean here? Well, the function is just this, x plus 2. So go inside the x plus 2 and make the x negative. It looks like this. Let me make some room for that. So h of x is going to become, okay, now f of x is this, but we're replacing x by -x. And so h of x ends up looking like that. It's a -x plus 2. So what's different between this and this? Well, here we have -x plus 2. Over here we used to have, or at least the previous step, we had a -x minus 2. So notice this function is different from this function. And by the way, it's also different from this function. These are 3 different functions. So what does this graph look like? This graph looks like, let's see, -x plus 2. Huh? That would be a y-intercept of 2, same y-intercept, except the slope is negative. So we're going through the same y-intercept, except the slope is -1. So it's going like this. It's going like this. So I'm going to call that my h of x. Right, h of x. So which way did we reflect? Not up and down. If it was reflecting up and down, this point at +4 would have to come down to here. That's what it did last time, but that's not what it's doing this time. This time, what it's doing is it's reflecting over the y-axis. It's a left-right kind of a reflection, see? So here I'm at x equals 3. I end up with an x equals -3 over here. Keep the y the same when you reflect this way. So here, I'm at this y level, right? But x is -2, bip it on over to x equals +2. That's how you do a reflection over the y-axis, which means left and right. Okay, so let's write that down. The effect of putting the negative there is a reflection over the y-axis, which means this away, that away. Okay, and actually we could put that summary right on the next page. So -f of x does in fact, let me write this a little differently. Usually what we do is we say, I'm making a new function with a new name. By taking my old function with the old name, taking the old f of x, I'm changing it this way. I'm putting the negative in front. That is basically multiplying the function by -1. This is a reflection. Remember, that was the first way we reflected. That's up and down. It's over the x-axis. It's up and down. Whereas if we, let's maybe call it h of x, if we did this kind of a thing, go inside your function and change all your x's to -x's, plug in -x in other words, then your reflection is over the y-axis, which by the way means left and right. So sometimes people see x and they automatically think horizontal, and so they think the reflection is this way, right? No, be careful, be careful. A reflection over the x-axis means you're reflecting over the x-axis, which means things up are going down and things down are going up, and so on. So anyway, That's our nice summary. So what's really valuable here is that you can take stuff like, you know, this nice little equation here and say, well, what must that graph look like? Now, this works best if you already have a nice familiarity of what that function looks like. That was lesson 56. I'm going to draw that function real quick, like, remember, and plus you can also just plug in values real quick and say, well, when x is 0, 0. When x is 1, I get square root of 1 is 1. When x is 4, I get, you know, this is my square root of x function. But what we've got is we've got the reflection over the x-axis. So keep this in your mind for a second, because we're going to erase it and we're going to draw it again, but underneath here, like this. So instead of 1, 1, I got 1, negative 1. Instead of 4, 2, I got 4, negative 2, and so on. So this is the negative square root of x down here. Here's a cool one. Maybe I'll get a cooler color. Now this time it's a square root of x. It's a version of square root of x. So keep that function in mind. This, ideally, you have this function almost memorized. 0, 0, 1, 1, 4, 2. These are some nice points on the square root of x function. But what this is, since the x is inside, this is a reflection over the y-axis, left, right, like this. So it's going to be over here someplace. So erase this one and then redraw it over here. Not 1, 1, negative 1, 1. Not 4, 2, negative 4, 2. Like it this. This would be the square root of negative x over here. Just as an aside, if you were to make an xy table, you would go something like this. Plug in x equals negative 1. Y is the square root of negative 1, which is the square root of 1, which is 1. Get it? It works. It works. Some people don't like that negative in there, but it's okay, because if you plug in x as negative, then the negative is going to be a double negative, which is going to make it positive, so no problem. Anyway, back to our little exploration here. What do we got going on here? This one's got 2 negatives. Well, that means you're going to reflect twice. Take the square root of x function, which looks like that, and reflect over the x and reflect over the y. And it doesn't matter which one you do first. It'll come out the same. So in other words, instead of doing something like this, I'm going to have to reflect it over there and then over there. Or if you want, you know, reflect it this way and then this way. Or if you want, reflect it this way and then this way. It's going to come out the same. So you kind of have this expectation. I'm going to be in the third quadrant, so the origin stays there. So instead of 1, 1, I'm over here. And instead of 4, 2, I'm over here. And so on. So there's your negative square root of negative x. Now, what's this one? This one's slightly interesting because, well, let's see, any new color. That's an interesting thing. It's a new color I could use. Oh, let's get gray. Okay. Remember, this is the one, whoops, this is the one that kind of looks like this with the crosshairs on the x-axis and stuff. Well, what's this going to do? It's going to flip it over. So these aren't moving. The axes themselves don't move. So the asymptotes are going to stay there. But instead of being up here, it's going to be down here. So remember, the reciprocal of 1 is 1, but we flip it over. The reciprocal of 2 is a half, but we flip it under. Reciprocal of a half is 2, but we flip it under, and so on and so forth. And you end up with this, and it's a nice symmetrical kind of a thing, so you can just kind of make little mirror image points over here, and there you go. Now what's interesting about this one is, I was just saying, oh yeah, that was reflected over the x-axis to make it upside down, right? But you could just as easily say, flip it over this axis. Right? You could flip it sideways. It would come out the same. It would come out the same. Why is that? That's because if you take 1 over x and you replace x with a negative x, well, guess what? That's the same thing as having the negative in front, right? So this is one of those situations where whichever way you flip it, you're going to get the same result. If you flip it over the x-axis, it'll come out the same as if you had flipped it over the other axis. And so anyway, that's just cute. Okay, so that was page 2. Okay, there's one other thing. As long as we're reflecting and we've already translated, we ought to look at like doing both at the same time. All right, slow down a little bit for this one. Perform the following transformations on the indicated functions and graphs. Okay, we've got a function Okay, we're going to do this. We're going to go left by 3, and then we're going to reflect over the y-axis. Okay, so here's the function. If I want to go left by 3, what am I supposed to do? Do you remember? This is from yesterday. If you want to go left by 3, you go inside the function, and you replace the x with an x plus 3. These are your instructions, so to speak. That's how you do a left by 3. Take whatever function you've got, go inside, change the x to an x plus 3. Okay, again, this is from yesterday. So what does that look like here? It looks like this. So the x inside has become an x plus 3 inside. Okay, cool. Now, reflect over the y-axis. Okay, so we want to reflect over the y-axis. Now we have to ask ourselves, how do you reflect over the y-axis? Well, that means a left-right reflection, and that's when you do this kind of a thing. Okay, we just saw that above. If you go inside your function and you take the x and make it into a negative x, you will reflect over the y-axis. It's a left-right reflection. And so that means go inside of here and make that into a negative x. So here's what our new function is going to look like. Now I could make an xy table, of course, to see what the graph looks like, but let me try to challenge you to try to make the graph without doing the xy table. How would you do that? Well, what you would do is you would do it in stages, and in this case I think gray is a beautiful color. You'd say, well, I'm starting with the absolute value of x, which is this triangle type thing at the origin, right? Doing this kind of thing. I should put arrowheads, but save that for later. Now if I move left by 3, that's going to end up over here, right? So it's going to end up over to here like this. That's my left by 3. And then to finish, get the blue out, to finish, I should reflect this over the y-axis. Over the y-axis means this bips on over to here. And it's going to look like a this. So try to picture this whole thing being reflected over the y-axis. This point, of course, ends up here. This point's on the y-axis, so it stays on the y-axis. This point way over here has to flip over to way over there, and so on. And so you end up with this blue thing over here on the right. Now, if you want to test yourself, you could say, well, let's just see now here. If I plugged in like x equals 0, what would I get? Negative 0 plus 3 is 3. Take the absolute value, it's 3. Yes, I have that point. What if I were to plug in x equals 3? Well, I'd have a negative 3 plus 3 is 0. I'd get y equals 0, which I do. It's right there. Yep, I get it. Okay, and then let's plug in one more. Let's plug in 6. If I were to plug in 6 in here, I'd have a negative 6 plus 3, which is a negative 3, but then you take the absolute value, you get a 3. Yes, you get this point. So yeah, it's working pretty good. It's working pretty good. So this is a good exercise to be able to do these transformations to the equations themselves is a good idea, but also just to the graph itself is a good idea. And of course the two things are related, which is what we're ultimately trying to appreciate here. Now this number 2 kind of looks like the same thing, except notice it's saying stuff in opposite order. Instead of saying left then reflect, it's saying reflect then go left. So it's the same two moves, but we're doing them in a different order. Well, first let's follow the action on the equation. So we're starting with the absolute value of x, just like we did last time. This is saying that first we should reflect over the y-axis. So remember how you reflect over the y-axis is you make x into a negative x. So that does this. Go inside the function, make x into a negative x. Yep, that's what that does. Now we're supposed to go left by 3. And how do you go left by 3? Well, we wrote it right up there. To go left by 3, you do this. Go inside the function and make x into an x plus 3. What does that look like? Go inside the function, and where I see the x right there, I make the x into an x plus 3. Remember, whenever you plug in, you always use parentheses. So it looks like that, or if you prefer, distribute that negative. It looks like that. Okay? is this equation the same as this equation? No, it is not. So is this graph going to be the same as this graph? No, it can't be. It's not the same equation. How could it be? It's different. Well, okay, we'll do an XY table in a second, but first, let's try to picture what happened here that's any different. We start the same. We start with just plain old absolute value of x, which is this 45-degree V thing starting at the origin, vertex at the origin. Now, if we first reflect over the y-axis, it's not going to look any different, is it? This point reflects over to there, this point reflects over to there. It's not going to look any different at all. So reflecting over the y-axis actually does nothing. So what's going to happen is you're going to then reflect it, you're going to then shift it left by 3, which means it's going to have to end up over here. So there's your final answer this time. Okay. And again, this function and this function are obviously different graphs, right? Different functions, different graphs. Let's just double check by plugging in, make a little XY table real quick. If I were to plug in x equals 0, I'd have negative 0 minus 3, which is negative 3, but then you take the absolute value and you get 3. Yep, that's that point. If I were to plug in x equals negative 3, what would that do? Well, now I'd have, plugging in a negative 3 here, this would be positive 3 minus 3, which is 0, and the absolute value is 0. So when x is negative 3, y is 0. Yep, we get that point, and then I'll let you verify this yourself. If you plug in negative 6, you will get a 3, which is this point right here, and yes, it's working. Okay, so one of the points to take from these two examples, looking at them together, is that sometimes it makes a difference. It looks like you're doing the same transformations. Hey man, I'm going left 3 and reflecting. Hey man, I'm going left 3 and reflecting. Yeah, but you're doing them in different order. And that's not always going to make a difference, but sometimes it will. Sometimes it will. How do you know if it's going to make a difference? Well, we can kind of summarize that right here. And I'll say if you mix left to right reflections with any kind of left to right translations, notice that's what both of these were. We were going left and we were reflecting over the y-axis. Or up and down reflections with up and down translations, the order will make a difference to your final result. If you go left 3 and then up, if you go left 3 and then reflect over the y-axis, if you go reflect over the y-axis, then go left, you're going to get different results. Not so if you mix something that goes up down with something that goes left right. If I go left and then up, or if I go up and then left, I'm not going to get any different results. So anyway, something to keep in mind. So sometimes this will happen. You're trying to get a function to move a certain way or whatever, or you're trying to read a function and say, which way did this end up moving? Sometimes you got to sort of be careful about, well, I see two transformations here, but which order should I be doing them in, because it can make a difference. Okay, them's our reflections.